So hello again. This is Roger Koch Barr for the Bioelectricity course. This is week 3, segment 7. This is a problem session, this segment, and I thought for this problem session it would be useful to examine the results. Let's just try to quantify some important details by looking at the graphs for the simulations. First, what are the peak values? We'd like to know the peak voltage relative to the baseline. That's what we're calling VM. We're using VM with the lowercase v as voltage against the baseline. What is the peak VM with a passive patch? And what is the peak VM with an active patch? Let's divide that up into 2 time periods, during the stimulus and after the stimulus. So what I'm asking you to do here is to go back, look at the graphs, and say, what was the peak VM for passive tissue during the stimulus? Well, it's something in the range of 10 millivolts. Go back and look and check and see if that's right. For passive tissue, for any time following the stimulus onset, that is to say throughout the whole entire waveform, what was the peak VM? Again, maybe 10 millivolts. Go back and check by looking at it. But in any event, these two answers are going to be the same because the highest voltage in passive tissue occurs just at the end of the stimulus. Now for active tissue, go back and look and say during the stimulus, that is towards the end of the stimulus, what is the peak voltage there? I thought looking at our curve that it was just a little bit higher. Please go back and check, but it's something like maybe 11 millivolts. Maybe it's 12, 15. Would you look, please, and see if you can get that? And then the active tissue at any time following the stimulus onset. Wow, this number is now a lot bigger, so maybe it's 100 millivolts. If you'll go back and look, please, carefully and fill in those numbers as they ought to be. Try to get them to the nearest millivolt. Although on the graph sometimes it can be hard to resolve it, but try as best you can to get them within the nearest millivolt. If we look at these results taken as a whole, of course the striking thing, the very striking thing, is what this difference is. 10 as compared to 100. Wow, active tissue, 10 times as big, more or less. We'd like to also ask the question for the duration, the time duration of each deflection on the waveform. The individual phases in this kind of work are often referred to as deflections, so that's why I use that word. First of all, what is the time duration of the stimulus current? That's fixed. And in this case, it's 400 microseconds. What is the total duration of the passive waveform? Not just the stimulus phase, but the whole entire waveform. Now that's a question that's a little bit trickier than it seems, because the ending is not very sharply defined. Let us suppose we just define it arbitrarily, by definition, as about 10% of the peak value. So when the waveform falls back to within 10% of the peak value, we will say that it's over. So for the passive VM duration, look at the curve and see how long you would say that would be. maybe it's around 2,000 microseconds. Or it could be longer than that. Look at it, please, and see what you think. And then for the active waveform, how long does it last? Now that's a tricky question again, because it lasts a while above the baseline, then it goes down below the baseline and comes back up. Let's suppose for the purpose of this question, we take only the part that's above the baseline. How long does it last until it comes back down to within 10% of the peak value? Please look back and see, and figure that number out and put it in here. So with this peaceful view of the cemetery at Orange Church, I will say that I think we should have some satisfaction at completing this segment, because we have seen some numbers that we can count on for action potentials, and on the other hand, we still have not solved the mystery. Thank you for watching. We'll see you next time.